By age 6, the physical size of a human brain has already reached 95% of its peak adult volume. Yet the executive function and advanced decision-making capabilities required of adulthood lag 15 to 20 years behind that physical plateau. Historically, the mechanics of this developmental gap remained hidden. Cross-sectional studies took isolated snapshots of different age groups, obscuring the continuous, subtle changes occurring within individual trajectories over time. The National Institute of Mental Health broke the stalemate by executing an expansive longitudinal dataset. Researchers tracked over 2,000 subjects, acquiring magnetic resonance imaging scans from the same individuals repeatedly at 2-year intervals. This tracking spans the entire developmental arc, from age 3 to 30. The resulting data proves that instead of uniform growth, the adolescent brain undergoes an asynchronous restructuring process defined by the divergent trajectories of specific tissues. To understand the profound cognitive leaps of adolescence, we have to stop measuring the brain's container and start tracking its internal wiring. This scatterplot charts longitudinal measurements of total brain volume. The data reveals a distinct inverted U-shape over time. Total volume peaks at precise, differing ages, 10.5 years for girls and 14.5 years for boys. But isolating a specific vertical slice on this graph, for example, right at age 10, reveals high variability along the y-axis. Within that narrow age band, one perfectly healthy 10-year-old boy can possess nearly twice the total brain volume of his peer. Across the pediatric ages, male brains average 10% larger in total volume than female brains. This discrepancy cannot be explained by body size, as male bodies do not outpace female bodies in growth until well into puberty. Morphological volume exists independently of functional advantage or cognitive maturity. Because total size fails to explain adolescent cognitive development, the true mechanism must lie in the shifting ratios of the brain's internal architecture. This chart tracks the specific trajectory of white matter volume. Note the robust, linear upward slope that continues straight through adolescence and early adulthood for both sexes. The physical driver is myelin, a fatty insulating sheath wrapped tightly around nerve axons by cells called oligodendrocytes. This triggers a 100 times increase in signal conduction speed. Because the ion gradient only resets at the uninsulated nodes, the neuron recovers 30 times faster. The combination of increased speed and quicker recovery time results in a 3,000-fold increase in the amount of information transmitted per second. This increase in bandwidth facilitates broad integration and rapid communication across disparate neural circuits. We can measure this functional integration physically. This graph shows the continuous upward growth of the mid-sagittal area of the corpus callosum, the main bundle connecting the left and right hemispheres. The linear rise in white matter is physical evidence of the brain upgrading its internal network from a localized system to a high-speed broadband network. This chart maps gray matter volume. It reveals a sharp inverted U trajectory that directly contrasts with the linear expansion of white matter. This volumetric decline is not tissue damage. It is an aggressive refinement mechanism known as synaptic pruning. Pruning is driven by Hebbian learning principles. Cells that fire together wire together. Only the heavily utilized neural connections survive this phase. Breaking the gray matter data down by lobar regions proves that this pruning does not happen everywhere simultaneously. It follows a distinct chronological sequence. This data on parietal gray matter volume shows an early curve peak. Primary sensory motor areas reach maximum volume and begin pruning earliest in the sequence, between ages 7 and 9. By contrast, this chart of frontal gray matter volume reveals a delayed peak, with pruning initiating later in adolescence. Higher-order association areas, specifically the dorsolateral prefrontal cortex, are responsible for integrating primary functions into advanced cognitive control. They mature last. The loss of gray matter is a vital sculpting process. By stripping away redundant synapses, the brain sequentially increases network efficiency from the back of the skull to the front. Adolescent brain development features an asynchronous imbalance between two networks. First, early maturing subcortical regions rapidly organize to process emotions and drive reward-seeking behavior. Second, late maturing prefrontal control networks remain under construction through protracted pruning and myelination. Adolescents possess fully mature sensory and reward capacities, but they lack the structural bandwidth in the prefrontal cortex to reliably inhibit impulses. This protracted period of mismatch is an evolutionary necessity. Extending the malleability of the prefrontal cortex is exactly what allows the human brain to adapt to highly specialized abstract reasoning and complex social structures. As individuals reach their mid-20s, myelination stabilizes and pruning completes, physically closing the structural gap between emotion and control. Rather than a defective adult brain acting erratically, the adolescent brain is a highly active, optimizing construction zone, fine-tuning its signal-to-noise ratio for adulthood.